Okay. Hi, everybody. So I'm Gus. I'm from University of Washington. And today I'm going to be talking about a little bit of work that we've been doing to help developers bring their own custom data types into TVM. So during this session, first I'm going to talk about why you should care about new data types and what new data types even are in the first place. Then some of the work that we've been doing to support data type exploration in TVM, which right now is just in software, but in the future will also be in hardware, and we'll talk a little bit about those directions at the end of the talk. And then lastly, of course, like everybody else, we're going to do a coding session in a Python notebook. So hopefully by now, I think we've motivated the need for deep learning accelerators. I don't really think anybody in this room needs to be convinced that deep learning accelerators are something that's exciting and something that we want to build. There's one more thing I do want to motivate that people might not be as excited about or might not even know about, which is the need for custom data types in deep learning accelerators. So I'm sure most of you are familiar with some of the common accelerators for deep learning. So the TPU is the first example that everybody thinks of. There's also Intel's Nirvana, and then there's there's VITA, which we've been talking about a lot today. One thing people might not know about these accelerators is that these accelerators are customized down to the levels of their hardware data types. So instead of relying on IEEE float to do real number calculation, they have their own methods and their own schemes for representing real numbers. And these new schemes, these new formats, are highly optimized for deep learning. So the TPU, for example, uses what's called the bfloat16, which people may have heard of. The Nirvana chip uses something a little bit more complex called the flex point, which is actually a really interesting type. I won't get into it, but there's a white paper about it you could read. And in VITA, in the future, we'd like to allow you to use whatever data type that you bring to the table in hardware. So before we go into new data types and why we want to use new data types, let's talk about what's wrong with IEEE floats in the first place. So IEEE floats are everywhere. All hardware nowadays pretty much has an FPU unless it's really, really simple. So if it's so widespread, why not just keep relying on it? It's been around for decades. Why not just keep using it? So the problem here a lot of the problems here have been highlighted by deep learning hardware specialization. So first off, IEEE floats, they take up a lot more space than is often needed. And in deep learning acceleration, you need all the space you can get. You often have giant weight tensors, giant activations, and you need all of that space that you can get. Research has shown that data types down to even size 8 bits or even less, like Megan was talking about, can be used in deep learning without losing really any training accuracy. Second, IEEE floats have pretty poor dynamic range. When I say dynamic range, what I mean for a number representation, its dynamic range is the range of real numbers that it can actually represent. So other new data types, non-IEEE floating point data types, can represent much larger and much smaller numbers with the same number or even fewer bits. And this is really important in the deep learning space because deep learning training depends more on researchers shown it depends more on the dynamic range of a number rather than the precision of the number itself. And then lastly, IEEE floats are the hardware that they require. Those FPUs are just overly complex. And the IEEE 754 spec is just notoriously complicated, and so the hardware required to implement it correctly is also correspondingly complicated. So let's look at what modern data types actually look like nowadays. First, we're going to talk about the bfloat, which I brought up earlier in relationship to the TPU. And the bfloat is really straightforward. It's basically just the IEEE single precision, but with the last 16 bits cut off. Those are all these fractional bits. And so when you cut off the 16 bits of the fraction, what you get in the bfloat is a number with almost the same dynamic range as the IEEE single precision 32-bit float, but it's half the size. What you sacrifice here by cutting off all those fractional bits is a lot of precision, but it turns out that precision doesn't really matter in the context of deep learning. So by cutting off that 16 bits, you basically save half the space almost for free. And the bfloat is used natively in the TPU. It's also used in some Intel deep learning hardware. You can use it natively in TensorFlow. So it's a pretty common new data type. Another data type that people may not have heard of, which is equally interesting, maybe even more interesting, is the posit. And the posit is a lot like the IEEE single, or a lot like the IEEE format in the sense that it has a sign, it has an exponent, it has a fraction. But the posit adds this regime field. And this regime field is this, it's encoded as repeating ones or zeros, so it can change in size. And the result of having this regime field is that if you have a small regime, so just down to 2 bits or less, you get a number that's close to plus or minus 1, and you get a lot of fractional bits, those gray bits. So close to plus or minus 1, you have a lot of fractional precision. Now, if you have a long regime, you get a number that's close to the extremes, close to the biggest numbers that can be represented by the posit. But you have no fractional bits, so you have no precision with those numbers. And so posits kind of hit both points of the spectrum in the sense that they have a large dynamic range. They're able to represent these numbers near the extremes, and those numbers can be very large if you have this large regime field. But you also have a lot of numbers close to plus or minus 1, and those numbers have high precision. So posits seem very promising in the deep learning space for these reasons, and there's actually a good amount of work for building posit hardware for deep learning and also training networks with posits. So given the popularity of deep learning accelerators nowadays, it's pretty clear that deep learning needs hardware specialization. But given these accelerators' dependence on customized data types, it's also clear that hardware specialization needs new data types. And so that's the motivation behind the bring your own data types work in TVM. Specifically, our goal is to make data type exploration really easy with TVM. This not only ends up helping data type researchers who need easy ways to test their data types, but more importantly, it ends up helping all TVM users who can easily use these new data types that these data type researchers come up with in their models. So they'll be able to just basically switch to using these data types as easily as you'd switch between float 32 and float 64. So now I'll go into a little bit more detail on exactly how we're allowing users to bring their own data types into TVM. Before we talk about exactly how you use new data types in TVM, let's look at how you use new data types in workloads without TVM, just to motivate the need for TVM here. So let's say there's a data type researcher who wants to build a new data type in hardware, or this could also be a deep learning researcher who wants to use a new data type in their model or whatever they're doing. So to prototype their new data type and to test its behavior, this researcher will first build a software emulated version of the data type. They'll build a library which implements their data type instead of just jumping right in and building hardware. This step is important. This step of building this library is what allows them to kind of test the numerical stability of their data type and how it's going to behave in large models. So once they want to use that data type in real workloads, what they're going to have to do is they're going to have to kind of hack apart that workload, and they're going to have to patch their data type into it. And as you can imagine, this process is really messy, painstaking, takes a lot of time, a lot of effort. So don't just take my word for it. We're going to look at an example in the wild of somebody actually doing this. So this is an HPC researcher's fork of TensorFlow. And they forked TensorFlow so that they could add posits into TensorFlow. And the result of it required 237 commits worth of work to add posits into TensorFlow, nearly 6,000 lines of code added to TensorFlow that touched a huge number of files across the code base. So this amount of work just to add posits into TensorFlow, would be prohibitive for most data types researchers. Obviously, there's some people out here who want to do this, and good for them, but most people probably don't want to do that. So if you don't want to go and hack TensorFlow, write 6,000 lines of code to add posits in, what should you do? So can we do better? Can we let users bring their own data types to TVM and have TVM do the rest of the work? So can TVM do the work of compiling big workloads to use custom data types? So now let's take a look at how you can compile big workloads to use custom data types with TVM. So out of the box, TVM doesn't know how to interpret a workload on the right that uses a custom data type like bfloats. But with a little bit of information, TVM can compile and run these programs pretty easily. So let's come back to this situation. We have our data type researchers. Our data type researcher, they want to run this workload on the right. It's using bfloats. Luckily, they have their bfloat library on hand. This is just like, let's say it's just a software emulated version of bfloats. So this researcher is just going to give TVM a little bit more information about their data type, and TVM is going to be able to compile and run their programs. The first thing that they're going to give TVM is they're going to give them this library. They're specifically going to point out the different functions within this library that implement the important functions over this data type. So your add, your multiply of a bfloat, your cast from bfloat to float, and vice versa. All of these important functions. And then they're also going to give TVM a little bit more information about the data type. Right now, all you actually need to give TVM is the size of each unit of the data type, so that's pretty straightforward. And then once TVM has this information, it can take all of this in, and it can actually go and compile, just with that information, it can go ahead and compile that workload. And that workload is going to end up depending very heavily on that software library that emulates the data type, because every time it hits a bfloat, an operation involving a bfloat in that workload, it's just going to call out to that library. So just to summarize this in text to make it even more straightforward, the first thing that the user does is they're going to make or find a library that emulates their custom data type. That's the very first step. We're assuming that they're bringing that with them, hence the name of the Bring Your Own Data Types framework. Then they're going to write a program directly using that data type. Additionally, they're going to point TVM to the important functions in the library and also give a little bit more information about the data type, right now just the size. And then finally, with all that information, TVM will be able to compile their program with their custom data types. And every time, like I said, every time it sees a bfloat, for example, it's just going to call out to that library. There are some limitations in this current approach that I wanted to just be upfront and clear about. Specifically, as you might have guessed, right now we're only supporting software implementations of data types, but in the future, my bad, hang on. In the future, we will be supporting hardware implementations. This is just it's a work in progress right now. Feel free to ask offline if you're interested in incorporating your hardware data type, using your hardware data type through TVM. And then before we go to the coding session, I want to just talk a little bit more about some future work in the data type space in TVM. So in the short term, what we want to do right now is we want to start doing some evaluation of real deep learning models with real data types that people are using nowadays, some real new data types, so posits, bfloats, et cetera. Additionally, so if you have a model or a data type that you're interested in, ask me about it afterwards. I can definitely help you get set up running that in TVM. And then additionally, in the short term, we want to improve the performance of this in software. As you'll see in the coding session, and as you might be able to imagine, calling into a software library that emulates data types, especially if it's at all a complex data type, can be really slow. But there's some basic optimizations we can add in TVM that should speed this up quite a bit. They're just not implemented right now. And then in the long term, like I said, we want to support custom hardware data types. Specifically, we're going to look into doing this in Vita, but in any accelerators, ideally. OK, great. Let's move over to the notebook. So here's our notebook. That first cell should have already run, so hopefully we're good here. There's a lot of text in this notebook. Go through it afterwards. There's a lot of reading to be done. I'm not going to obviously read all of this to you, but this notebook should be good for reading afterwards, getting more detail out of it. We've looked at a lot of TVM already today, and right now I'm going to show you what is an incredibly basic TVM program. It's a little embarrassing, honestly, after everything we've looked at, but we're going to just go through the simplest example that's going to use new custom data types. We're literally just going to add two vectors together. So if you haven't seen what this might look like writing this in TVM, this is the code that creates that program. So we instantiate these two placeholders. They're vectors of size 3, and then we're just going to add them together. So that's our basic program. We can define that program, and then we can go ahead and we can schedule it, lower it, and build it. And so that's the program we get out. And as you can imagine, we can also then, we're going to create inputs for this, and we're going to create the output to hold the output, and then we're going to go ahead and run that program. So as you might expect, TVM can do this simple add. So now let's actually change this to use custom data types. Let's take a look at what using custom data types in TVM actually looks like. So here's what we're going to do. We're actually going to just, right now what we're going to do is we're going to redefine the output of that program. So if we go back up to Z up here, so Z was just the add of X and Y, the input. We're going to change Z to use custom data types. It's still going to be an add, but what we're going to do is we're going to cast the input X to a B float. We're going to cast the input Y to a B float. We're going to add them, and then we're going to cast that result back to a float. And this is the syntax for basically specifying that you're using a custom data type here. So we're just saying we're using this custom data type called bfloat, and the size of the data type is 16. And that's exactly how you specify the size, like I was talking about in the slides. So when we try to make a program like this, as you can imagine, TVM is going to complain at us saying that a type named bfloat is not registered. We haven't actually told TVM about bfloat, so it's not really going to know what to do here. So what we do is we go ahead and register that data type. And this 129 is just a type code for this custom type. Right now, at the early stages of this framework, this is just chosen arbitrarily. You just choose it yourself. But in the future, we'll probably have some kind of registry for types. So we go ahead and register our data type, and then we're going to rerun that code. And now TVM doesn't yell at us. We can actually declare this program. Now, when it comes time to actually build the program itself, so let's also look at this code for building. If we go back up to our simple program, to actually build the program, we first created the schedule, we lowered that schedule, and then we built that lowered schedule. So in the data type space, what we do is we do the same thing. We create the schedule and then we lower it, but we have this one more step, which is basically running this pass to lower the custom data type. So this program right now includes these bfloats, which TVM doesn't necessarily know how to interpret. So this pass, what this pass does is it goes through and every time it sees a custom data type, it lowers that to something that TVM actually understands. And I'll talk about how this is done in a bit. So right now we manually run this pass, but in the future you won't have to worry about doing this manually. It'll be incorporated into this whole build process. So let's now try to actually build and lower this. As you can expect, we get another error. And what's this telling us? This output message is, the English on this is a little unclear. I apologize. I was going to change it, didn't have time. But what this is telling us is basically that the lowering function for lowering our custom data type operation isn't found. And this kind of tells us what TVM is doing under the hood. Every time TVM encounters our custom data type, it looks for a lowering function that tells it how to lower that custom data type. So in this case, it's saying it can't find the cast lowering function for destination type 129, which is our bfloat, source type 2, which is just a normal float. So it's looking for a cast from a float to a bfloat. And it needs a lowering function to tell it how to lower that. So what we're going to do is we're going to tell TVM exactly how, we're going to give it that lowering function. So that's what we do with this TVM data type register op call here. So what register op does is it takes a lowering function as its first argument. And this lowering function basically will take a piece of IR that you're lowering. So in this case, we're going to be lowering a cast. this function will take that cast and turn it into a new cast that does not involve custom data types. To do this, to create lowering functions easily, we've supplied this helper function for the common case. So in the common case, what you want to do is if you see a cast, or if TVM sees a cast, you're going to want TVM to lower it to a call into your library. So I have this library. This library knows how to do a cast from a float to a B float and vice versa. So what I want is I want to turn this cast into a call into that library to the appropriate function. And that's exactly what this create lower func helper function does. It creates a function that turns this cast into a call into a library. And this syntax there's a lot of arguments here, but the important parts are just giving TVM this lowering function, telling it that it's for a cast. Target is the actual target you're compiling for, so LLVM in this case. And then this cast is for casting from a float to a B float. Basically, this is how you tell TVM exactly which lowering function this is. So we go ahead and we register that lowering function, and we can now try to rebuild. So when we rebuild, we get a new error. It's a different error this time, and it's basically it looks very similar. It's just telling us that the add lowering function for LLVM type 129 is our B float. It's this time that's the lowering function that is not found. So no longer is it complaining about not finding the cast. It's just complaining about not finding the add. So as you can guess, we're just going to repeat the same thing we did above. We're just going to register the operations for the other. We're going to register the B float operations for the other operations in this program. So in this case, we're going to register the other cast. So before we registered the cast from float to B float, now we'll register the cast from B float to float, and then also the cast for an add of 2 B floats. So we'll just go ahead and register those. And then finally, we can actually build this program without any errors. And so this is the program this is the IR that's returned. Let's go ahead all the way down to the bottom and take a look. And so you can see now that this program is just being implemented with calls to that library. So we have this float to B float 16 wrapper, which I didn't show you the source code for, but it's in TVM itself. It's just a kind of a toy implementation of B float, and that's the function that we're calling out to. And likewise with all of the other operations that we're implementing here. By the way, stop me at any time if you have any questions. I know we're moving a little fast. And then finally, we can run that program. And as you can imagine, it's going to give us the correct output. And I'll just run the two together. So here's our input, our x and our y on the first 2 lines. This is the output in float 32 land. And then as you can see in the B float land, we are close to that, but not exact, just due to the actual limitations of B float precision. So you can see this is being run through the B float library as expected. Okay, great. So that is, in a nutshell, how TVM handles custom data types in this framework. Oh, but one more note, by the way. So I told you that the B float library is included in TVM, just this kind of simple toy library. If you want to use your own library, all you need to do is have it compiled as a shared library and then import it into TVM this way. You just need to, import it into Python as you're running your TVM code this way. You just need to expose those functions within that library, and all of this code will work just the same. Okay, so that was how we run a simple program using custom data types. Now, really quickly, I want to kind of move into more. This code is more experimental. This is kind of like the alpha code right now in the data types framework. Everything I've shown you so far, you can go out and do right now in TVM. All of that is merged into mainline. What I'm going to show you right now is purely testing code, but it's a bit more exciting because this code is an example of how we can run an entire model with custom data types, which is what people really want to see in the end. Like I said, this is really in the alpha stage right now. There's been some issues with data type numerical stability, which is just something I need to work through. But all in all, this portion of the tutorial is meant to show you what it's going to look like to run a model using custom data types. And it should look a lot like what we saw before. So Part 1, we used bfloats. Now we're going to use posits. There's a little description of posits here, but we already learned a lot about posits earlier. So let's take a look at how we actually convert a whole model to a custom data type. So TVM has models packaged specifically within Relay, within tvm.relay.testing. There's a lot of models packed up in there. We're going to be using MobileNet as our model. It's one of the smallest ones that Relay provides conveniently. And we're using MobileNet. We're using a small network specifically because, like I said before, this code right now is very slow. If you're running emulated data types, as you might expect, it's very, very slow. So MobileNet is one of the only things that runs in a reasonable amount of time. And it doesn't even run it in a reasonable amount of time for me to show it during this demo. So you can run the last cell of this notebook on your own and wait the 10 minutes for the inference. So we can run MobileNet pretty straightforward, just 4 lines or just 3 lines to just using Relay's graph execution engine. And that'll give us this output. So now we want to take MobileNet and we want to change it to use posits internally, just like we did for our simple program. So we'll go ahead and we'll register our posit type. And now we need to actually convert the network. To do this, first we're going to define this helper function, this convert ND array. And what this does, it's going to be a helper function that will convert our tensors from float to bfloat. This is just something that we need to do, for example, to change all of the input parameters, all the weights that come pre-trained with MobileNet. We're just going to use this helper function to convert all of those to posit. So there's our helper function. And then this is really where the interesting stuff happens. This is where we actually convert MobileNet to use posits. So what we're going to do is we're going to use this helper pass that we wrote in Relay to change the data type to posit. So we define our source data type. It's coming from float 32. Our destination is posit 16. Right now, the custom data types framework only works if you simplify inference first. You don't have to worry about this. It's just an implementation detail. So what we're going to do is we're going to change this network to use custom data types. So we first infer the type here, and then we're going to run this change data type pass here, and then we'll infer the type again, just to show that first we had float 32s, and then everything gets changed over to posits. And then finally, we're going to try to convert the parameters. This is going to produce an error down here, which we'll go through and explain exactly why. So we'll run this code. OK, great. So here's the original MobileNet. As you can see, this is using float 32s. And it looks like MobileNet, like Logan said before. It looks MobileNet-y. There's a lot of conv2ds and everything. But if we go down to the bottom, here is now MobileNet with all of its data types changed to posits. So it's the same exact program, but in the end, everything is actually changed to this custom posit type. OK, great. So we've changed MobileNet over to use posits. But we also, at the very end of this, we get this error. We're getting the same error that we saw before, in fact. It's saying that cast lowering, basically the cast lowering function for posits is not found. So we know how to do this. We need to register the functions we need to tell TVM how to lower posit functions. In this case, because this is an entire model, there's going to be a lot more things that we need to register. And so this is kind of the main difference from the example above. We need to register a lot more actual operations. We need to tell TVM how to lower a lot more operations to actually implement this model. But there's still a lot of the things that you might expect. So before we just had the 2 casts and an add, all we really had to implement were some other primitive operations. So subtraction, multiplication, division, a max operation, square root, and an exponential, and then an if then else. So pretty straightforward stuff. And we've also included this it's within my branch of TVM, but we're using this small bfloat wrapper library that's actually depending on a posit library from Stillwater Supercomputing called Universal, which is a great library if you want to check out posits. So we register all of these functions. And then finally, we can convert those parameters again. So these are all the parameters of the networks, all the weights, the pre-trained weights. We'll convert all of those using that convert ND array helper function that we had before. And we convert our input as well to posit. And then this last box, like I said, I'm not going to run this because it takes a long time to run. You can go ahead and run this on your own. But essentially what it does is it runs our model, our converted model, on our converted input using the converted weights. And this will pop out a result in the end. And everything will have been internally run with posits. And there's a few directions we want to go with this. We want to be able to accept, posit input raw, for example, instead of taking float 32s and converting them first. But that is, in a nutshell, how you use custom data types in TVM. Thank you, everybody.